Hello chemistry students, today I'm going to review how to solve heat transfer and calorimetry practice problems. So the first thing to know is that when you are solving heat transfer problems, it means that you're solving for Q, or you're trying to find the amount of heat that's been absorbed or released by a system. And in order to calculate that value, you need to use the equation Q equals Sm delta T. And in order to solve calorimetry practice problems, usually what you're doing is you are trying to find the specific heat of an unknown metal, and in order to do this, you need to fill out a data table, and you need to do 2 QSMAT problems. And when you're doing these, the thing that you have to remember is that negative Q of the water, Q of the water, my mistake there, is equal to negative Q of the metal. But we'll get to that in a little bit. First, let's practice our heat transfer problems, which utilizes Q equals Sm delta T. And here on this page, I give you different values. For instance, the specific heat for water is always 4.18 joules per gram Celsius. You need to remember that 1 milliliter of water equals 1 gram of water. And then you also need to remember that in order to find delta T, you need to subtract the final temperature and the initial temperature. Okay, let's get started. So for number 1, how many joules of heat are needed to raise the temperature of 10 grams of aluminum from 22 to 55 degrees Celsius? Well, this is a heat transfer problem, like how much heat is needed. So we're going to use our equation Q equals SMAT, Sm delta T. So we're looking for Q. We know that our specific heat of aluminum is 0.9 because I give it to you in the problem. I know that the mass of our aluminum is 10 grams. And remember that delta T is equal to TF minus TI, or T final minus T initial, which in this case is 55 minus 22, which gives us a difference of 33 degrees. So I'm just going to plug that in here. And when I multiply 0.9 times 10 times 33, I get 297 joules of energy, and that is my answer. Okay, let's take a look at our next one, which is number 2. So if 100 milliliters of 4 degrees Celsius water is heated until its temperature is 37 degrees Celsius, calculate the amount of energy needed to cause the rise in temperature. So again, we're looking for the amount of energy needed to change the temperature. So again, we use Q equals Sm delta T. And we have our S for water, because that's what we're using here, is 4.18, and I know that from the values that I gave you at the top of the page. The mass of water is equal to the volume of water, so this is 100 grams. And then we have delta T. This time, our delta T, and again, that's T final minus T initial, is equal to 37 minus 4. So again, we have a delta T value of 33. And so I'm going to plug that in right here. When I multiply all of these out together, my final answer is 13,794 joules. All right, and then let's look at one more problem here. Now, instead of energy being absorbed by a substance, we want to know how much energy is released when 85 grams of lead cools from 200 degrees Celsius to 1 degree Celsius. And then I gave you the specific heat of lead here. So once again, since I want to know how much energy is being transferred, and remember, transferred means being released or being absorbed, then Q is equal to SM delta T, which is equal to the specific heat of lead, which is 0.129. The mass of my lead is 85 grams. And then my delta T value will go right here. So now delta T is equal to T final minus T initial, and it's being cooled. So my final temperature is 1 and my initial temperature was 200. So in this instance, my delta T is a negative 199 degrees. But that's okay. I'll explain that in a minute, but we're going to go ahead and put that in here with negative 199. Remember that if your delta T is negative, it means that energy was released by the system. Okay, so when I multiply all of this out, I get negative 2182.04 joules. The problem is that when I ask you for a quantity, like how much is released, we don't say that it's negative. All that we need to do for our answer here is just remove the negative, and we have 2182.04 joules. You know, it's kind of like saying, you know, how many cans of beans are on a shelf at the grocery store. If you go to the bean aisle and you don't see any on the shelf, you wouldn't say, oh, well, I have a negative 586 cans because 586 cans are how much can fit on the shelf and they're missing. No, you would just say you have 0 or you have none. So our quantity, when I'm asking you how much, you're never going to include your negative sign there. You can simply remove the negative sign and then just report it as 2182.04 joules. Okay, so we're going to skip these and let's move on to our calorimetry problems. So with calorimetry problems, you have what you're doing is you're taking a block of an unknown metal, you're heating it up, and then you're putting it into cooler water in a calorimeter. And you're going to measure the amount of energy it takes for the temperature of the metal to equal the temperature of the water. And that's the Q for water. Then we're going to use that in order to figure out what the specific heat of the metal is. So like I said at the very beginning, if you know the specific heat of the metal, you can determine the identity of the unknown metal. So let's start by reading our problem, and then we're going to fill out the data table with the information that we have from the problem. A 23.9 gram sample of iridium is heated to 89.7 degrees and then dropped into 20 grams of water in a calorimeter. The temperature of the water rises from 20.1 degrees Celsius to 22.6 degrees Celsius. Calculate the specific heat of the iridium. Okay, so that's our problem. Let's fill out our data table here. So we already know that the specific heat of water is always the same, and that is 4.18. The mass of our water is 20 grams. Our final temperature of the water is 22.6 degrees. And our initial temperature of the water was 20.1 degrees. Our delta T, and remember that that is T final minus T initial is 22.6 minus 20.1, which is a 2.5 degree difference. So that's everything that I've got for the water. Now for our metal, we know that the mass of the metal is 23.9 grams. We know that the initial temperature of our metal is 89.7 degrees. And we know that the final temperature of the water, I'm sorry, I wrote that in the wrong spot. I know that the final temperature of my water is equal to the final temperature of my metal. So that is 22.6. Now remember that delta T is T final minus T initial, so this is a negative 67 degrees. Oh, sorry, it's actually a negative 67.1 degree. Okay, so the very first thing that we have to do is first find our Q for water, because if you look, we can't just figure out specific heat, because we need to use our equation Q equals SM delta T. And for our metal, we don't know Q and we also don't know S. So we can't directly figure out the mass of the metal or the Q of the metal. We need to first figure out the Q for water. So I'll just put a W there for water. So what this is simply 4.18 times 20 times 2.5. And when I multiply all of that out together, my Q of water is 209 joules. Well, the thing to remember is that the Q of water is equal to negative Q of the metal. You see, because my Q for water was positive, that means that the water absorbed energy from the metal. So conversely, the metal had to lose energy in order to give it to the water. So that means that my Q for metal is negative because the metal is losing that energy. So we know then that the Q of the metal is equal to SM delta T. So now I'm going to be using these values. I know that the Q of the metal is a negative 209 joules, and that's equal to the specific heat of the metal, which is what we're looking for, times the mass of the metal, which is 23.9 grams, times delta T for the metal, which is negative 67.1 degrees. So negative 209 is equal to S, and when I multiply 23.9 times negative 67.1, I get a negative 1603.69. Now to solve for S, I have to divide both sides by negative 1603.69. And when I do, I get positive number, because I'm dividing two negatives, 0.13. That is my specific heat for my metal. So I'm just going to put it up there. And then if I was in a lab situation or something, I would simply look at a reference table and find out what kind of metal has a specific heat of 0.13, and that's how I would identify my metal. So once again, in order to do calorimetry problems, you have to first read the problem, fill out your data table, figure out Q for water, and then plug in Q for water as Q for metal, but you just have to remember to switch the sign, and then you can find your specific heat of the metal. All right, let's do one more problem together. So for this one, if 100 grams of nickel at 150 degrees Celsius is placed in 1,000 milliliters of water at 25 degrees Celsius, the final temperature of the water would be 26.3 degrees Celsius. So what is the specific heat of the nickel? So let's do water first. We know that water always has a specific heat of 4.18. We know that the mass of the water that we're using is equal to the volume of water, so we have 1,000 grams of water. We know that our final temperature is 26.3, and we know our initial temperature is 25 degrees. And when I subtract these two, my delta T value is 1.3. And remember that delta T is T final minus T initial. Now let's fill out what we can for the metal. Well, we already know that we're looking for the specific heat of nickel, so we're not going to fill anything out in this box. The mass of our metal is 100 grams. Our final temperature is 26.3. But our initial temperature of the nickel was 150 degrees. When I subtract these two, I get negative 123.7. And so again, that negative sign means that our nickel lost heat to the water. So in order to figure out our specific heat of the metal, I need to do two Q-SMAT equations. First, we need to find the Q of water and then plug it into Q-SMAT for the metal. So Q of water is equal to SM delta T, which is 4.18 times 1,000 times 1.3. And when I multiply that all together, my Q for water, or the heat that was gained by the water, is 5,434 joules. Now, we know that Q of water is equal to negative Q of the metal. So we are going to plug in 5,434 joules in for my Q-SMAT for the metal. Let me write that better for you. Okay, so remember that we do not know S, but we know all the other variables, so we can definitely solve for S. So the Q of the metal is negative 5,434, and that's equal to S times the mass, which is 100 grams, times our change in temperature, which is negative 123.7. So we have negative 5,434 is equal to S times 1,237, and that's a negative 1,237. Now to solve for S, divide both sides by negative 1,237. I made a little mistake here. So actually 100 times negative 123.7 isn't 1237, it is 12370. I thought that number was a little small. Okay, so anyway, after adding my 0 there, now I can do my division. And so my S value is 0.44, which is equal to S. And then I can just plug that up here. And if you're ever wondering what the units are for the specific heat of something, they are right there, joules per gram degree Celsius. Okay, so let me just, since I just told you what this means is that nickel, in order to raise 1 gram of nickel by 1 degree Celsius, you need to use 0.44 joules of energy in order to increase the temperature of that sample. All right, chemistry students, that is all for this. Sorry about that little math error, but I hope that this helps you understand how to solve heat transfer problems and calorimetry problems. See you in class.